the work I will present is joint work done by Mathieu Montin and Amélie Agda, who is in the room. So the subject is nested data types, which have been widely studied during the last past 25 years, both theoretically and practically. For example, in programming languages like Haskell or in theorem provers like Coq. And our motivation here is to study a family, a specific family of nested data types, and to study more precisely functions and properties that can be automatically obtained. By automatically, I mean at a low cost. And in fact, this work started by the fact that Amélie was looking at some nested data types, and more precisely on induction principle. And then we moved to this objective. And so the contribution in the paper is called a modest library. We have called it LIBNDT. And it is about this family, and more precisely the spreadable properties of our families. And I will explain what I mean by spreadable in some next slides. So this library is written both in Agda and Coq. The reason why is very simple. The authors are coming from different communities, so we wanted to benefit from that. And it is available on GitHub. So the roadmap is very simple. I will introduce our family of nested data types, and then the functions and properties that are spreadable, and then I will conclude. So in the set of parameterized data types, usually we distinguish regular data types from nested data types. So regular data type is data type where the type parameters always the same in the type definition, and the classical example of list and tree illustrate that family. And in nested data types, the type parameter changes from the types in nature, and at least in one of its instances in constructor. So it's the case, for example, for nest and bow, where here you have the type parameter A, and here you have the Cartesian product A times A. And as the extreme example we can say is bush, because here the type parameter is A, and in the second constructor, the type instance is the type itself. So we will generalize this kind of definition by abstracting the type transformation performed on the type parameter, and we will focus on list-like data types whose elements can be viewed as a structure having a head and a tail, and it defines completely our family. And we call this kind of nested data types linked nested data types, as data types parameterized by a type transformation and whose constructors are very similar to one of the list type. So more precisely, I give you here the definition in Coq of the index type corresponding to this data type. So in the following, you will mainly see Coq code, and it will be written in black, and sometimes you will have Agda code, and it will be written in blue. So here the indexed data type is parameterized by the type transformation, and it is also a type transformation, as the definition is just something taking a type in as a parameter and giving a type as a result. And as you can see, it is very similar to the list constructors. So you have the empty one, which is of type LNDT of A, and the node constructor takes an element of basic type A, and the tail as a type LNDT of F of A. And in fact, as you will have a collection of elements, the first element is of type A, the second one is of type F of A, the third one is of type F of A, F of A, and so on. So some examples. We can define as inhabitants of this type. So you have the list. The regular type can be seen as an LNDT with identity as type transformation. The nest, so we have seen previously. And then we can generalize to what we call perfect trees. So we just have to define the notion of tuples. And then using this transformation, we have the n perfect trees. So it is an indexed type. And it means that why do we call them perfect? Because given such an n at a certain depth, we have either no child or children, or exactly an n+1 children. And again, we can define list and nest as instances as a perfect tree. And in the following, I will consider this view. And here you have an example of a nest nut. And it's awful written like this, but you can see here you have a natural number, a pair of natural number, a pair of pairs of natural numbers, and so on. We can chain LNDT. So as I said previously, so if we have a transformation F, type transformation F, then LNDT of F is also a type transformation. So we can chain them and we call them multi-layered LNDTs. So it is a case, for example, for the squared list, which can obtain by using the list defined as an instance of LNDT as a type transformation. And we can give also an example of a squared list nat. And I won't read this one, but use this friendly notation, more friendly notation. And here you have a list. So it will be this constructor, in fact. And you have three elements. The first one is nat element. Here it is a list whose single element is 1. And here you have again a list whose single element is the singleton 1. What about Bush as an instance of LNDT? So you have a reminder of the definition at the top of the slide, and it cannot be written in Coq as an instance of LNDT, and it cannot be written directly. If I try to write down this inductive definition in Coq, we cannot have it because of positivity restriction, sorry. And in Agda we can, but we can, if we turn off the termination checking, of course, because of the recursivity and so on. But we will do it for the rest of the talk, and so it's very easy to define the Bush instance. So we just use the Bush as a type transformation, and we can construct different elements, different examples. And of course, it isn't safe. And we can give such a definition in order to have a safe one, and it is accepted both in Agda and Coq, but it doesn't enter anymore our family, and it becomes an indexed data type where the natural number here records the number of times we have applied the type transformation. I can go to the next one.
I think you must have right-clicked.
So I will close this part by giving you this picture. So it is a picture of all the inhabitants of LNDT type we have defined. So I've spoken about most of them. I don't have spoken about this part, but it is quite trivial and kind of degenerated cases. So null can be so it is the unit type. It can be seen as a type transformation, and then we can construct maybe based on null as an instance of LNDT. So just until now. Okay, nothing more than I can do in Haskell or Camel. Now I would like to speak about properties and theorems. So the questions we are trying to address here is no, sorry, it was not the right introduction. So here I am only on function, and I will not speak about properties. So the question is what kind of functions can be expressed for LNDTs when we try to see them as collections. So what about map, fall, and style, and so on? And furthermore, we would like to have them at a low cost. And the questions we address here is, can these functions be obtained for LNDT F if they are available for F? And we call such functions spreadable functions. So map is such an example. So we would like to define map for LNDTs. That is a function that applies the function f of type A arrow B on each element of a structure of type LNDT F of A, and obtain a value of type LNDT FB. So we start by specifying what it means for a type transform. We start by specifying what it means for a type transformation to be mappable. So it means that if we have a function from defined from A to B, allows to obtain a function from f of A to f of B. And map is spreadable. So if you look at this expression of the time, it is the same exactly as what's written here in Coq. So it means that if you have a map on the type transformation, then you can have a map on LNDT F, that is the nested data type based on the seed we have given here. So the text of this function is very close to what you could write for a simple map on list. So in the case in the general case, we of course apply the function on the first element, and then we have a recursive call to obtain the rest, the tail of the structure. But instead of applying f, we apply map of f. And so the only thing we have to do is to define map on the seed, on the type transformation, to propagate it to the nested data type. So here is an examples. So you define the map on tuples. Then remember, we had perfect trees based on the type transformation tuple. So we obtain by this generic function the map for the perfect trees, and then we obtain freely just by choosing the right size, the map for list and nest. And here you have an example where we map this function on our previous example. And here is the result. Yes. Okay. And we do the same for fold. Okay, so we can spreadable in two ways. We can obtain the generic fold right and the generic fold left in the same manner. And again, for having the examples, again, it's the same. So if we come back to Bush in Agda, nothing to do, it's magic, okay? Because the seed is the type itself, so we don't have to define on the seed. And believe me, it computes. So what about the properties? So we have exactly the same question as for functions. So what kind of predicates, what kind of properties we will be able to propagate from the seed to the nested data types. So let me start by the universal satisfaction. So we would like to write the predicate that check that a certain predicate P is satisfied by every element in the nested structure. So we first specify what it means to be predicate transformer. So predicate transformer takes a predicate over A and provides a predicate over F of A. And we can define the LNDT OR, for example, which have this type, and it means that it is spreadable, because if you have a hole on the seed, so on the type transformation, you can have it for as a nested data type dependent on it. And again, you have a definition which is very similar to the one you would like to write on a list or a tuple. And again, the example. So I think you can follow easily the tuple. So you get it on the perfect trees, then you have it freely on list and nest, and then the applications. And the application here is a proof, okay, and it is very easy. It's just LEA for people to apply. Sorry. Maybe here something which is more interesting. So how can we preserve decidability properties? So we have, for example, proved here that if we have a whole predicate which is decidable on the seed, then it is also decidable on the nested data types based on the type transformation. So what we need here is not only to have a type transformation and predicate transformer, we also have to specify what it means to be decidability property transformer. Again, you can read quite easily. So if you have a predicate B, if it is decidable on A, then it is the transform predicate is decidable on F of A. Well, it's finished. We can also propagate properties about our spreadable function. So here we can propagate map congruence property with the same mechanism. And so I would like to skip to this one. So here you have the overview. We have the overview of all the property and function we have defined. And just a few words about the future work. We have two directions. The first one is to have more specification for the previous functions and predicates I have seen to you, because for the moment we don't have many semantic properties, and we would like to have some of them and to show that they are spreadable, and also more spreadable function and predicates. And we would like to go into two directions. I think, for example, how can we have generators, for example, using Coq quick check. So if we have a random generator for the seed, how can we have freely the random generator for the nested data types? And it would be very useful just to show you examples. And the last thing is how can we go to another family? Because of this one are not in our family, because you can see here we have three constructors. Here we have not anymore a constant, but a unary constructor. So, okay, it is out of reach for the moment. And if we want to go to this family, do we want to do the work again? No, I don't want. So I can abstract, but it will not be so concrete. And so we will be far from our preoccupations, and we can try to use meta programming or something like ornaments. But ornaments have difficulty to handle parameters. So certainly meta programming would be the case. Thank you very much, and sorry for the delay.